Fourth grade lesson 6.1 is equivalent fractions. And I know for a lot of you, when you see fractions, you get a little nervous, maybe panic a little bit. That happened even when I taught upper grade math. People will get a little nervous about fractions, but fractions are good, especially when you're sharing things. So I'm hoping that as we get through this section, I can help you feel much more comfortable about fractions. And I want to start this lesson before getting into equivalent fractions, just doing a very quick review, and the show what you know kind of already did that, but doing a very quick review of the pieces, the anatomy of a fraction. So a very quick look back at what the show what you know was. With the vocabulary, we have the numerator is the top part of the fraction. It's the partial part that we're talking about when we're looking at something that's being split apart. And the denominator is the bottom part of a fraction. That is all of the pieces that could be there but maybe aren't. All of them that are or are not there that are possible. So in this section, this candy bar, let's call it, we split it into 4 equal pieces. So all of the possible parts that were there in the beginning was 4. Out of those 4, how many are shaded in? Just the 1. That's the part. That's the numerator. So 1/4 is shaded in. On this one, the denominator is representing all of these equal parts. Remember, it has to be equal parts. Pretend that's all equal. I tried the best I could to draw it equal. 1, 2, 3, 4, 5 equal parts that are divided up. Of those 5 equal parts, how many are shaded? Just the 1. That's your numerator, 1/5. So 1/5 is shaded. Of this shape, how many total parts are there? There's 3 total parts. Of those 3 total parts, how many are shaded? Just the 1. How many are shaded here? I'm sorry, not shaded. How many total are possible here? 1, 2 equal parts. Of those 2, how many are shaded? 1. This is all fractions are representing. So if we had a cake cut into 1, 2, 3, 4, 5, 6 equal pieces, 6 equal pieces, 6 equal pieces. That's how many total pieces were there before people came and ate them. If the shaded part represents how many pieces got eaten, 5, 6 got eaten. And on this one, how many total pieces are there? Denominator is 5. Of the 5, how many are shaded? 2. Okay, that's all fractions are. They're just splitting stuff up into equal pieces, and then whatever you have, that's the denominator, and then whatever you have left is your numerator. Now that we've reviewed fractions and what those numbers, the numerator and the denominator, are representing, let's take a look at the investigate problem and see if we can tie that together with what equivalent fractions are. This activity, you can get paper out and cut it up the way you need to for this if you need to actually see it happen with paper, or you can just use this. It's up to you. Joe cut a pan of lasagna into third-size pieces. He kept 1/3 and gave the rest away. So he cut it into 3 equal pieces. 1, 2, 3 equal pieces. He kept 1 and gave the rest away. Joe will not eat his part all at once. How can he cut his part into smaller, equal-sized pieces? They want us to draw on the model to show how Joe could cut his part of lasagna into 2 equal pieces. You can rename these 2 equal pieces as a fraction of the original pan of lasagna. I'm going to circle that because that becomes important. So they say suppose Joe had cut the original pan of lasagna into equal pieces of this size. So we were just cutting this one to 2 equal pieces, but we have to include the whole original pan. So we would cut down here like that. How many pieces would there be? There would be 1, 2, 3, 4, 5, 6 total pieces before he gave any away. What fraction of the pan is 1 slice? 1 slice now is 1 out of 1, 2, 3, 4, 5, 6. 1 out of 6. And what fraction of the pan is 2 pieces? It's 1, 2 out of 6 total. So what we notice is 1/3, when it was just 1 out of 3, 1 whole piece out of 1, 2, 3, it ended up being the same when we cut them into smaller pieces as 2 out of 6 pieces. So that means they're equivalent. He's not changing the amount of lasagna now that he has 2 slices. He doesn't get more lasagna. It's just 2 slices of smaller pieces, We cut it up some more. It didn't change the amount. I'll use another example before we go to the next one. Let's say I had a coconut cream pie, which is one of my favorite types, and I split it into 2 equal parts, and I was going to share that with Luis. So Luis gets 1 out of the 2 equal pieces, and I get 1 out of the 2 equal pieces. And that's it. He only gets 1 slice, right? Let's say I did that same thing with that same coconut cream pie, but instead I cut it into 4 equal slices. And I'm going to give Paulina 2 slices of that pie. So she gets 2 slices of that pie. Is Paulina getting more pie than Luis because she's getting 2 slices and he's only getting 1? No, right? She's getting the same amount of pie. She's still getting that amount of pie. It's just that I cut hers into smaller slices. So 2 of them is what would put together to equal the 1 of his when we had bigger slices. So these are equivalent fractions. I'm not changing the amount. I'm just changing how I cut them up. And you'll notice that the more I cut them up, the larger this denominator gets, the smaller the pieces get. If I took that same pie and said, hey, I'm going to let AJ have 4 pieces of pie. Oops, let me change that pen color. 4 pieces of pie. But I had cut it into 8 equal pieces. He's still getting the same amount as Paulina and Luis. They're still getting the same amount of pie. Luis isn't getting ripped off here only because he got 1 slice. He got 1 huge slice. Paulina got 2 good-sized slices. And AJ's getting 4 smaller slices. All the same amount, though. It's 4 out of 8 cut-up pieces instead of 2 out of 4 cut-up pieces, or instead of 1 out of the 2 cut-up pieces. It's equal in their amounts. We're just cutting them differently. That's what equivalent fractions mean. Now that you kind of have that tied together, let's look at this next example. They want us to draw on the model to show how Joe could cut his part of lasagna into 4 equal pieces. Remember, this is his part of lasagna. So we're going to cut that into 4 equal pieces. But remember I circled original here. If I'm cutting this into 4 equal pieces, I'm cutting even the gone pieces kind of in my mind up so that I know what my denominator will be. So we'll cut across here, here, and here. And I'm going to darken these lines here and here. So now he's cut his 1 slice into 4 equal pieces. I had to account for all of the gone ones too, though, because I cut this whole thing up differently. How many pieces total? What's my denominator? There's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And of those 12, how many pieces? Smaller pieces, right? But how many pieces does Joe have now? He has 1, 2, 3, 4. 4 out of the 12. So there would be 12 pieces. What fraction of the pan is 1 piece? 1 out of the 12, right? 1 piece of the new cut up amount is 1 out of the 12. What fraction of the pan is 4 pieces? That's this amount, 4 twelfths. So 1/3 is the same as 4 twelfths. So equivalent fractions is all about the same amount of pie or candy bar or whatever, just cut in different ways. Okay, they want us to draw some conclusions. They want us to compare the models for 1/3 and 2/6. I'll draw that real quick again over here since we switched pages. How does the number of parts relate to the sizes of the parts? So here we had 1 out of 3 shaded in, and here we had 2 out of 6 shaded in. How does the number of parts relate to the size of the parts? So the number of parts relate to the size of the parts. Here we had 1 part out of the 3 bigger parts, and here we had 2 parts out of the 6 smaller parts. So we find that even though we had more parts, they're smaller because they're cut into more pieces. So how are the numerators and the denominators related in 1/3 equaling 2/6 being equivalent, being equal? Well, if we notice our numerator, it doubled. I multiplied it by 2, right? Because I cut it into 2 equal pieces. So that would mean that probably this must be doubled 2 or multiplied by 2 also in order to become 6. So 1 times 2 is 2 and 3 times 2 is 6. And what you'll notice in that pattern is that whatever I do to the numerator of this, if I do the same thing to the denominator of that, then it will stay equivalent. So here, if I multiply 1 by 2, I get 2. As long as I multiply 3 by 2 also, then it would be 6. Then I stay equivalent. So I just wrote here, they both doubled. The numerator doubled and the denominator doubled, meaning they both got multiplied by 2. Well, let's take that same reasoning. Does 1/3 equal 3/9? Well, what do I multiply by 1 in order to get it to become a 3? I would multiply it by 3, right? If I multiply 3 times 3, does that equal 9? Yes. So as long as I multiplied them both by the same thing, the numerator by the same thing as the denominator, I'm going to remain with an equivalent fraction. And I'm going to draw that so that your brain can see it. Okay, so I've drawn the 1 out of 3 for the 1/3. Now I'm going to take this 1/3 and I'm going to cut it into 3 more pieces each. So I have 3, 6, 9 here. I'll use a different color just so that we could see that. There's 3. Pretend these are equal pieces. I'm not real good at that. It looks like a mad face. All right. Now I need 3 out of those 9 pieces. 1, 2, 3. So here was the 1/3. And here is the 3/9. 3 out of 9 equal pieces. 1, 2, 3 shaded out of 1, 2, 3, 4, 5, 6, 7, 8, 9 equal pieces. Are they equal? Are they equivalent? Yeah, that amount is the same as that amount, right? So what I did was tripled each of these pieces, 3, 3, and 3, and it still had 3 of these equaling this one big amount, but now I have 9 equal pieces instead of 3 equal pieces. So we can answer yes, it's equivalent because everything tripled. The numerator and denominator tripled, or times 3. So I just wrote yes, because both the numerator and denominator, I ran out of room, tripled, or times 3. To both. I can't do times 3 to one and not the other. That is going to throw me off balance. But I can do it to both, and it will stay equivalent. As long as I'm fair and I don't leave one of them out, I will keep these numbers, these fractions, equivalent. All right, let's go on to the make connections section of this. We have a story that we're looking at, and they're going to kind of walk us through and help us make some connections here. Savannah has 2 out of 4 yards of ribbon. So we've got yards of ribbon cut into 4 equal pieces. She has 2 of those 4 yards of ribbon. And Isabel has 3 out of 8 yards of ribbon. So she has a yard of ribbon that's cut into 8 equal pieces. And out of those 8 equal pieces, she still has 3 of them. How can you determine whether Savannah and Isabel have the same length of ribbon? The equal sign, equal, and the not equal sign, equal with a slash through it, is not equal, show whether fractions are equivalent. So that's how you will signify if it is equivalent, equal sign, or not equivalent, the not equal sign. We need to tell whether 2/4 and 3/8 are equivalent. We will write the equal sign for equal, or the not equal sign for not equivalent. They want us to shade the amount of ribbon Savannah has. I want to point out to you, just make this comparison on a number line, because this is something that I know a lot of my kids, when they were in the upper grades, struggled with. They hadn't made this connection at a younger age, and I want to help you do that. I'm going to do a regular number line, and I'm going to put 0 here and 1 full here. When we're talking about fractions, we're talking about the between 0 and 1 on the number line. A fraction is not a whole 1. It doesn't make it to the full 1 unless we have the full amount of the denominator. So I'll use this picture to help. We took between 0 and 1 on the number line, zoomed in. So here's the number line 1, 2, 3. We zoomed in between here. We broke that into 4 equal pieces. 1, 2, 3, 4. 4 equal pieces. 4 equal pieces. I'll draw that. 4 equal pieces. I did 3 dashes because this counts as a dash. 1, 2, 3, 4 equal pieces. I'm breaking one whole up into 4 equal pieces. And then I'm going to count out of those broken up 4 equal pieces how many I cross over. So you can see 0 out of 4 pieces puts us right at 0. And 4 out of 4 pieces, when we're talking about the denominator being 4, that's the entire amount, and there's 4 of them, that means everything is still there. So that would be 1 on your number line. When you have the numerator and the denominator the same, that's one whole. So again, we're focusing in, when we're talking about fractions, we're focusing in on between 0 and 1. So we have 1/4, 2/4, 3/4, and 4/4. 1/4, 2/4, 3/4, and 4/4. So we're going to shade the amount that Savannah has. She has 2 4s. Let's shade that in. 1/4 and 2 4s. Now let's look at the amount of ribbon that Isabel has. Remember, she had 3 out of 8 cut up pieces. Remember, if we're looking at the number line, we're looking at 1 yard. So just between the 0 and the 1 yard of ribbon. We cut it up into 8 equal pieces. 0 out of 8 means none of them. 8 out of 8 means the whole yard, 1 full yard. And here's all the in-between pieces: 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8. She has 3 of those 8. So we're going to shade in 3 of those 8. There's 1, there's 2, and there's 3 of those 8. And so now that I have them all lined up, I can compare them which one has more, or if they're in fact equal. They just asked if they're equal or not, if they are equivalent or not. Is 2 4s equivalent to 3/8? And if we draw that line straight up, look at, not quite, right? 3/8 is a little less than 2 4s. So I'm just going to say here that they are not equivalent. Now let's look at the share and show. They want us to use the model, this model compared to this model, to write an equivalent fraction, an equal fraction to this one. So we can split them up in several different ways. I have 1 out of the 1, 2, 3, 4, 5 pieces as 1/5. So looking at this model over here, right now it is the same 1 out of the 5 pieces, right? But if I split this evenly, even just right there, like that, let's say, now I have how many total pieces will be my denominator? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as my denominator. And 1, 2 of those 10 are shaded. That's still equal. So 1/5 is equivalent to 2/10. And look at, I doubled the numerator, also doubled the denominator. That's how you can kind of tell that I have an equivalent fraction. Let's do that again. I have 2 out of 1, 2, 3 equal pieces here, 2/3. How can I split that to keep it equivalent? Well, I'm going to go big on this one. I'm going to make this a lot. You could do less if you want. I'm going to go like that. This is all equal pieces. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 equal pieces. And out of those 12 equal pieces, 2, 4, 6, 8 of them are shaded. So 2/3 is equivalent to 8/12. Take a look. What do I multiply 2 by in order to get it to become an 8? 2 times 4 is 8, right? So as long as I do 3 times 4 and it equals 12, I know I have stayed equivalent. That's how you can really recognize equivalent fractions. If whatever you do to the numerator, you do the same to the denominator, you're cutting them both up the same way. So you're still good. And this last part, they just want us to just tell whether the fractions are equivalent or not. Are they equal or not? And I'm going to do this both ways, and you can kind of fast forward where you need to or don't need to. I'm going to do it as a model first, so your brain can see it. Let's do our brains a favor until it kind of makes those connections. But then I'll also talk about what we multiplied by. Did we multiply the numerator times the same thing as the denominator to get to that answer? So sometimes that works. Sometimes it's not as obvious. Like if you look at, well, it is kind of obvious on number 6 too. Let's go ahead and do this one first. 1/6 being compared to 2/12 as a model first. Okay, here I did 6 pieces. And here I did 12. I took those 6, and 6 times 2 is 12, right? So I just divided them up into 2 parts each. And now I'm going to highlight 1 6 and 2 12s. And looky there, they're the same. 1 times 2 is 2, and 6 times 2 is 12. So I multiplied my numerator and my denominator both by 2. And so they are, in fact, equivalent. Oops, I need a pen there. Equivalent, equal, equivalent. Okay, how about this one? 2/5 being compared to 6/10. Take a look at that one and see if you could tell just by looking at the relationships here while I draw this out. Okay, I've cut one piece into fifths for this one, and then I doubled it for the tenths into fifths, and then I did in between to make 10 equal pieces. And now I'm going to highlight them. On the first one, it's 2/5. And on the second one, it is 6/10. 1, 2, 3, 4, 5, 6. Oh, yeah, if you take a look at there, if you draw this line up, that is not equivalent. And if you noticed, you may have noticed this, 5 times 2 gives me 10, but 2 times 2 is not 6. Or maybe you said 2 times 3 is what gives me 6. But this is not 5 times 3 is 15. So they didn't do the same thing to the numerator as they did to the denominator. So it won't be equivalent. Unless you do the exact same thing, unless you're fair, it won't be equivalent. You've got to be fair. Check number 5. Notice, though, I can't do 4 times anything to get 1. Use the reverse of multiply, then do division. Or come to this side and do 1 times what gives me 4, and is that same amount that way. You can go either way. You can reverse it. So try that one while I draw it. Okay, now I've drawn it. I have my 3 equal pieces for this one, and then I have my 3, but then I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for that one. I'm going to color in one of my 3 for this one. That's for this one. And 4 of my 12 for this one, and look at it's exactly the same. And if you look at it in reverse, 1 times 4 is 4, and 3 times 4 is 12. So yes, those are equivalent. You're probably at a point where you're not necessarily needing the pictures anymore. I will still do them in case you do. Let's take a look at 5/8 compared to 2/4. These are bigger, so I'm going to start on this side instead. And I'm going to see if these are equivalent. I'll start with my denominators and then look at my numerators. All right, and if you're not seeing it right away, here's the drawings of those. I did the 4ths here and the 8ths here. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to color in 2 out of the 4. 1, 2 for 2/4. And then I'm going to color in 5 out of the 8. 1, oops, that's the wrong color. I want to do that. 1, 2, 3, 4, and 5. And look, that's more up here. You could see that that's not the same amount. Those aren't equivalent fractions. And you may have noticed without the drawing, because 4 times 2 is 8, but 2 times 2 is not 4. So as soon as that doesn't work out, then you're not equivalent. Let's look at this one, and I will draw it, but we're going to start by looking at it just as the numbers. I'm seeing that 6 times 2 gives me 12. Does 5 times 2 give me 10? So this would be equivalent. Let's draw it just to see. All right, there we go. We have 5 out of 6. 1, 2, 3, 4, 5. And we have 6 out of the 12. 1, 2, 3, 4, 5, 6. Oh, sorry, we have 10 out of the 12. I was confused. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Trying to confuse us all. Sorry about that. They're equivalent. Which we notice by now. I hope we're starting to notice by now. If I multiply the top by one number, and if I multiply the numerator times one number, and I multiply the denominator times one number, the same number, then it will stay equivalent. We have 1/2 and 5/10. Well, let's look at that denominator first. 2 times what number is going to give me 10? 2 times 5, right? Is 1 times 5 5? Yes. So those are equivalent. We'll do the picture for your brain. You don't have to draw the picture. I'm just drawing the picture so your brain can see it. There's our drawing, and we have 1 out of 2 here, and 5 out of 10. 1, 2, 3, 4, 5. Same amount, equivalent fractions. Nobody's getting more candy bar than the other. It's fair still. So it is equivalent. Oops, that's the wrong thing there. There we go, equivalent. So that's what this lesson's all about. Hopefully that clarified everything for you and you're able to tackle this. Good luck.